Hi, in this video I'm going to solve another example of compound interest, how to use this concept within this formula we got here on the left. And well, let's get to this thing. Now in the setting we have again Matt. This guy likes to invest, I could say. So Matt's planning to buy a car in 3 years again. So he wants to invest again 5,000 and now, but now the best 5,000 now and hopes to have 6,000 to spend on the car when he buys it. Now, what kind of interest rate would he need if his investment were compound monthly? We can see that pretty much everything remains the same, but now we have a final value because he hopes to have one day, luckily, he has $6,000. So and he's investing an initial value of again 5,000. Now let's see. We have sorry, I'm going to use a different color for this one. Would be in this case A, it's equal to 6,000, which is his goal to buy his car. So P, which is the initial value, in this case P, it's again 5,000. And he's got a he's planning to buy a car in 3 years. In this case, this would be our time. So T, it's equal to 3. Now, we know again that this investment is compound monthly. So that is to say the N will be equal to 12. And now, as you can see, the thing we're lacking here is the interest rate in this formula. It's actually the question, what kind of interest rate would he need if his investment were compound monthly? So we do not know the the interest rate. So let's write this down in the formula and let's see how we can work this out to solve this out using algebra. It will be here a 6,000, it's equal to 5,000, which is a final amount, final value, it's equal to the initial value times, will be here 1 plus, now the thing we do not know, it's our R. It's our R, which is R, it's equal, it's over N, which is again 12, all raised to, I'm going to raise to 12, which is N again, times the time, which is equal to 3. There it is. This is a very ugly 3. There it is, better. So I'm going to simplify this out as much as we can so we can see things more clearer. So I'm going to divide the left and the right side by, so I'm going to use a different color here. There it is. I'm going to divide this one over 5,000. There it is. And I'm going to divide the right side as well over 5,000. I'm canceling out the 5,000 on the right. And now this one, 6,000 over 5,000 is just equal to 1.2. So we got that 1.2, it's equal to, it's equal to 1 plus R over 12 raised to the, we can simplify the exponent, which is 12 times 3 will be 36. And now, the thing is, how can we find out this R? Actually, we don't even have to use logarithm. We should just only use something we actually found. We used a long time ago, since a long time ago. If I would like to find the value of, let's say, x cubed equal to 1, if I would like to to get done with this exponent, and we have to get the square root on both sides, now we get that x is equal to the square root, we have the cubic root of 1, which is equal to 1 in this case. X is equal to 1. Now that is to say, I have to raise to a power. This power, the cubic root will be equal to raising 1 to 1 over 3. Now, this principle can be used to any number and any power. So we can even use it something as big as a 36. Now, every time we have an even power, just keep in mind that if you have x squared, it's equal to 1, and you get the square root of this one, the result that you will get will have two possibilities, plus minus. The square root of 1, which will be equal to plus minus 1. So technically, if I raise this both sides of the equation, let's say write it like this. If I raised both sides of the equation to the 1 over 36 power, like this, both sides of the equation to the 1 over over the 36 power, I would get in return a plus minus result. But the thing is, this is a real life problem. So as this is an interest rate, there cannot be an interest rate in this case that would be negative. So we just have to consider in this case the positive one. So we can just pretty much cancel out, forget about the negative result and just consider the positive one. But the thing is, by multiplying this 36 times the 1 over 36, which is an exponents operation, you will get this raised to the 1th power. And well, basically, and now the thing is, solving out the one on the left, 1.2 raised to the 36 powers, it makes looks complicated, but with a calculator it's actually quite nice. So on the left, this would be equal to 708 point need more space here. 708.80, and let's leave it like that. Say 801. I think that's nice enough. And now here on the left, we'll get rid of this 36, so it will be 1 plus R. Oh, sorry. This 708, that's totally wrong. I'm sorry. I'm going to. This is not cool. I'm sorry. I'm going to. So 1.2 raised to the 1 over 36 power is actually something near to 1. Yes, it's 1.005. Let's write like this, 1.005. There it is. Now we have to solve here. We have to cancel out this one. So I'm going to subtract 1 on both sides of the equation. It would be -1. So we got to subtract -1 on the other side. So we'll get to this nice operation will be 0.005. It's equal to R over 12. Now this I have to multiply now for 12 on both sides of the equation. So it will be times 12 to cancel out this one. So and on the left, will be multiplying by 12 again. So we'll get at the end that R will be equal to 12 times 0.005, and that will be equal to 0.06, which in other words means that the interest rate has to be equal, let's say interest rate has to be equal to 6%. So if Matt wants to buy a car in 3 years and he wants to invest 6,000 and hopes to have 6,000, he wants to invest 5,000 and hopes to have 6,000 to spend on a car when he buys it, the interest rate he would need to have, it would be 6% of this interest rate compounded monthly. And basically that's will be all with this exercise.